product of the two numbers had to be 192. So we were at the point where we wrote the primary equation, which was the part of the problem statement that involved the thing we were trying to maximize. We're trying to maximize the sum. The problem is that the primary equation is a function of two variables, and we don't know how to deal with two variables. So we use the secondary equation. So the third step is to reduce the primary equation to one having a single independent variable. This may involve the use of the secondary equations relating the independent variables of the primary equation. So these are the independent variables of the primary equation. We have two independent variables, but we have this relationship. So we can either solve for y in terms of x, or we could solve x in terms of y. It doesn't make any difference. You'll still get the same answer. So what I do is I solve this secondary equation for y, and then I substitute in the primary equation. So when I do that, the primary equation becomes just a function of x. And then I will take the derivative of that with respect to x and find the values where ds dx equals 0. And those will be my possible points of maximums or minimums. You see the equation's not that hard. Before we do that, though, we have to look at the domain. And so the domain would be, one thing is positive numbers. It doesn't say that here, but it's in the actual problem statement in the book. It says positive. What two positive numbers? And it's probably not going to be anything greater than 192. It's going to be somewhere in between. So the main thing is that it's a positive result as far as the domain is concerned. So let me erase this part right now. Oh, this was just to show if you wanted to do it the other way. So we could solve for y, make this equation here in terms of x, or we could substitute x and make it in terms of y. And you can see the equations are very similar to each other. In this case, we're going to either take ds dx or ds dy, depending upon which one we do. Okay. So the fourth one is determine the feasible domain of the primary equations. And in this case, I just said that x had to be greater than 0 and y had to be greater than 0. So if we get a negative solution, we'll say that's not within. It's like in physics, if we get a negative time, we know that's not good. Okay. So let me erase that and start over again. So then what we do is we're going to take the derivative of this equation. So let me go back. I'll pick this one. So we'll take that, we'll copy it. I don't know why I did that. I mean, paste it. Let's try it again. Paste. Where the heck is paste? Oh, there it is. Paste. Okay. So now we're going to take the derivative of this with respect to x. So ds dx. And because we're taking the derivative of these with respect to the variable x, and the derivative is, so the variable's x, we're taking the derivative with respect to x. It's just the normal differentiation rules. Before I do that, though, I'm going to rewrite this as x plus 596 times x to the minus 1 power. Okay, so now I'll take the derivative. You get 1 plus negative 1 times 576 times x to the minus 2 power. And so ds dx equals 1 minus 576 divided by x squared, putting that in the denominator. And then you set it equal to 0. And then we find the values of x where this is 0. So we can multiply everything by x squared, and you get 0 is equal to x squared minus 576. X squared equals 576. X equals plus the square root of 576. Normally we would do plus or minus, but because the domain is limited to positive numbers, we're going to just use the positive root. So the square root of 576 is 24. So that's 24. And then to find the other variable, we just go back, just like we normally do. You go back to this equation that we used initially, this substitution, oops, I didn't mean to do that. This substitution equation that we used to rewrite the primary equation in terms of one variable. So we can just take that equation, put it back over here, paste it. So now that we know x, we know y. It's 192 divided by 24. 192 divided by 24, and that's 8. Okay, so that's your solution. And if we picked any other value of x, let's just prove that this is true. So if I did the sum was, what was the equation for the sum? X plus 3y. I've got x, which is 24, plus 3 times 8, which is 24. So that's 48. So that's the sum. That's what we're trying to maximize. Now, if I picked any other number than 8 or 24, let's say I let x equals 20. Well, if x equals 20, y is equal to 192 divided by 20. 192 divided by 20, 9.6. And so this is another solution without maximizing it. It satisfies the constraint. And then if I calculate the sum, I'll get 20 plus 3 times 9.6. And so we get 20 plus 3 times 9.6. You get 48.8, which is greater than 48. Because we were saying we're determining the minimum. In this case, it's the minimum value. So this is our minimum. So I've tried on one side of 20. If I went to 28, I could do that, and I'd find that was also greater than 40. So this does give me the minimum. One last thing is you have to confirm whether it's a minimum or maximum. It's supposed to be a minimum, but so I'm going to use the second derivative test in this case. We know it's a possible minimum or maximum. So we have to use one of this first or second derivative tests to determine that. So ds dx was equal to 1 minus 576 over x squared. So if I take the derivative of this, so I take the second derivative, I need to rewrite this with the negative exponent before I take the derivative. So you'll get 0 minus 2 times 576 times, so negative 2. Actually, it's a negative. There's a negative from here, and then you get negative 2 from the exponent. So negative here, negative 2, 576, x to the minus 3 power. So that gives you 1,152 over x cubed. So that's the second derivative. And for x greater than 0, ds squared dx squared is going to be greater than 0 because I have a positive number divided by a positive number gives me a positive number. So because the second derivative is positive, that means that it's going to be concave up like that. Therefore, x equals 24 and y equals 8 gives me a minimum sum. So it is a minimum. Anybody got any questions on how that works? So we've used both the first and second derivative test. The first derivative test to find the values of x. Well, actually, we used the critical numbers to determine the possible points that were minimums or maximums. Then we used the second derivative test to figure out whether it was a minimum or maximum. In this case, it was a minimum. We eliminated any solutions that were outside of the domain of the problem statement. Okay, so I got a handout, which is you guys are going to do one just like this, except with a slightly different twist. Got 4 optimization problems to work on. Turn my thing off before I walk past. So it has the, well, no, it doesn't. Let me. So you see it's 2 positive numbers. So that's how the domain gets restricted. So it says the sum of the first number squared and the second is 27 and the product is maximized. So what they've done is they've switched which equation is the one we're trying to maximize. So the product, which is x times y, we'll call p equals x times y. We're trying to maximize p. So the secondary equation is the first sentence, the first part of the sentence. The sum of the first number, which we'll call x, squared, and the second, plus y, is 27. Okay. So you'll need to then solve the first equation for either x or y, and then substitute that into the second equation, and then take the derivative of that equation with respect to whatever variable you decided you were going to rewrite the primary equation in terms of either x or y. So once you do that, then you take the derivative of that expression with respect to the variable, the derivative you set equal to 0, and then you figure out the values of x or y that cause the derivative to be 0. And then you also look at the second derivative of that equation and see whether it's positive or negative, concave up or concave down. So I'll put, I guess most everything, well, I don't have quite I'll move back. If you didn't take good notes, I'll move back 1 page and give you a few minutes to think about how you would set this thing up. Actually, there's too many pages to set it. I'd go all the way back to these 2 pages. That's the first thing. So I'll give you a few minutes to think about that. Make sure you got your equations right. Okay. So what you're going to do is you're going to solve this for either x or y. Probably y, well, yeah, it might be, well, I was going to say it might be easier to do the other one because this is not squared. So if you solve for y, well, if you solve this one for y and substitute it in, then it will be, I think it'll be easier than solving for x and substituting in. But you don't solve for, the product is actually given. I mean, pardon me, I'm wrong. My brain's wrong. Let me look at it again. Okay. So this is the constraint. So you're going to have to solve this for either x or y. And then you're going to plug it into here to make the product. So you're going to have p equals something, but the something has to be just a function of x. So if you solve this one for y, this equation for y, and then substitute it in, that's what we're looking at doing.
Does it have to be for y?
Yeah, or it could be for x. Let me see what you did. Okay, solve for y. Well, actually, you did what I just said. So you solve for y, substitute in, so it's a function of x. Then you take the derivative. So you're doing fine. Yeah, so give this some kind of name, like p. So that's we're trying to maximize the product. So you're going to solve this equation for either x or y. Probably y is easiest because you'd have to take a square root if you did it the other way. So then you can substitute that in to here for y, and then that whole side will just become a function of x, and then you can take the derivative of that. And it's easier because it's just a polynomial. This one's actually easier than the last one because you don't have to deal with fractions and stuff. Yeah, so before you take the derivative, go ahead and multiply out. Don't use the product rule. Just you're going to have 27 minus x squared times x. So multiply that out, so you'll get x cubed and something, and then take the derivative.
So multiply by x for this one? Or
Yeah, let me see what you're doing. Okay, let me see what you're doing. Like, what is going on?
No,
You did. You substitute the primary equation into the secondary equation, but you need to substitute the secondary equation into the primary equation and get it in terms of one variable. So I was reading this. I saw this article about, or something, they figured out, somebody has figured out what the Las Vegas motivation for the Las Vegas shooter was, and it was pretty good. Um, it was some guy who was anti guns all his life, but he never told anybody, and he realized that the only way to get something to happen was to have a terrible incident happen that didn't involve somebody who was mentally ill, a terrorist. And so he took it upon himself as his civic duty to decide to kill all these people so that people would know, the usual excuses for for not doing anything about gun control would not be valid. And they're saying this is the only possible solution to the whole thing. And somebody's like, is some guy who's not even ever said anything about gun control going to be a guy who's going to sacrifice his life for a cause? So it was a good conspiracy theory. It's interesting how people can come up with crazy things to make it look like it's all those liberal gun. It's the other guys. It's the opposite of what's really going on. That's kind of okay. So if you take the derivative of this with respect to x, you get that. Set equal to 0. Solve for x. Use only the positive solution. And I get x equals 3. And then you can go back to the equation that we used for the substitution. Y equals 27 minus x squared. So y equals 27 minus x squared, which is 27 minus 9, which is 18. So you get y is equal to 18 and x is equal to 3. And then the question about is it a minimum or maximum, what you would do then is take the second derivative. So you'd get negative 6x. So you can see for x, it actually says maximum. So that's why I was just like, this is not a minimum. For x greater than 0, the second derivative is going to be negative because I've got negative 6 times a positive number. So it's negative, which means, so for x greater than 0, the second derivative is negative. Therefore, it's concave down, which means it's sad face, and which means it's a maximum, which is what it says it was going to be. Okay, let's continue on here. Let's look at another. So I'm going to show you another example. So that would have been that's another example, but we're going to skip over that for right now. So the next group of problems involves kind of geometry and algebra. So it's kind of like the one that you're going to work here in a second, but let's go through this. So problem 15 says, find the point on the graph of the function that is closest to the given point. So what we have is we have the function y equals x squared, and we have the point 2 comma 1/2, which is right here. And they're asking what point on this curve is the closest to this point. I mean, just visually looking at it, let me just put this on one page. If I were to eyeball it, I would say it's that point. Because this point's further away. From this point to here is further away than this point to there. And if you take a point over here, that's further away. So it's going to be some place about there. So it's going to be around 1. But how do we do that using calculus rather than just kind of guessing? So we have to come up with the primary equation and the secondary equation. So if we read this, it says, find the point on the graph that is closest. Well, closest means the smallest distance. So in this case, our primary equation is the distance formula. And what we have is we have some arbitrary point x, y on this curve. So that the coordinates, there's some x coordinate and a corresponding y coordinate that satisfies this relationship. So what we have 2 points. We have x, y on the curve, which is variable. That's what we're trying to figure out. And the point x0, y0, which in this case is 2, 1/2. So if we want to find the distance between these 2 points, you'd use the distance formula. Distance is equal to the square root, in this case, of x minus x0 squared plus y minus y0 squared. So that's, you've seen the distance formula forever. And so this is what we're trying to minimize the distance. Notice the primary equation has 2 variables, x and y. So we need a secondary equation that relates x and y. So our secondary equation, so this is the primary equation. Our secondary equation is the function. Another word for the secondary equation is the constraint. So we're constrained such that y is equal to x squared. It has to satisfy that restraint. So we can plug in y in for y, we can put in x squared into this equation. So let's go ahead and do that. So you get distance is equal to the square root of x minus x0 squared plus, in this case, y is equal to x squared. So we have x squared minus y0 quantity squared. And let's go ahead and plug in the numbers, the actual x0 and y0. So you have x minus 2 squared plus x squared minus 1/2 squared. So now we have the primary equation in terms of one variable. And then you have to take the derivative of that with respect to x, which looks kind of hard. So does anybody have any thoughts about what we might be able to do? We don't really care what the distance is. We just want to minimize it. So is there any simplification that we might be able to make in finding the values of x? You could do that, but let me give you an example. I'm going to write something down to kind of make you think here. So let's say if 8 is less than 9, then the square root of 8 is less than the square root of 9. Okay? So if I say that I'm minimizing, I'm saying this is less than that. So this is the minimum comparatively speaking. But if I just compare these two, I'll come up with the same conclusion as far as, if this is less than that, then this is less than that. So what can I do with this square root thing? I can just get rid of it, okay? Because if I find the minimum for the term in here, the square root of that is also going to be minimum. So instead of doing d, I'm just going to call it d star, and I'm just going to minimize the argument of the square root. And that'll give me the same answer, and I won't have to use the chain rule and all kinds of crazy stuff. So it just makes it the algebra better. Okay, so I'm going to minimize this thing. And so I'm just going to multiply everything out. So I'll get x squared minus 4x plus 4 plus x to the fourth minus x squared plus 1/4. So, x times x is x squared. You get negative 2x twice. You get negative 4x. Negative 2 times negative 2 is positive 4. Same thing here. This squared is that. You get x squared times a negative a half plus x squared times a negative a half. It gives you negative 1x squared. And then negative half times negative half gives you positive quarter. So what we end up with is x to the fourth. These cancel out. Minus 4x plus 9, not 9, 17/4. So that's what I'm going to minimize now. So you take the derivative. If I take the derivative, unfortunately I have the same letter here, but the derivative of d star with respect to x, what I'll end up with is 4x cubed minus 4 plus 0. So that's my first derivative. I set that equal to 0. And I can divide by 4, so I'll get x cubed minus 1. Does anybody remember how you factor that cube thing? This is something you probably learned in Algebra 2, maybe. What's that? Say it again. Same opposite, always positive. Oh yeah, I never thought about that. Yeah, I think I see what you're saying. So, so what that means, I'm going to write the answer and see why that makes sense. So, you end up with that, right? Is that what it is? So you take, you have x minus 1 is one factor, and the other factor is the same. So you got x squared, 1x squared plus 1x plus 1. This doesn't have any solutions because there are no real roots to this equation. Another way of doing it, if you didn't know that, is you do the Mr. Pell approach, which is assume one of the answers is 1. And if you use synthetic division, you bring this down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. You get 0. So that's one of the roots is x minus 1, and the remainder is x squared plus x plus 1. Okay, so either one of those. So what that tells us is that the first derivative is 0 when this is either 0 or this is 0. Well, this is never 0. So you get one solution, which is x equals 1. And then you can plug that back into your, the y is equal to x squared is the constraint. So y is equal to 1 squared, which is 1. So, so the answer is x equals 1, y equals 1. And then if I take the second derivative, you'll see that what I get if I take the second derivative of d star is you'll get 12x squared. So for positive x, so if x is greater than 0, the second derivative is greater than 0, which means concave up, which means minimum, which is what we're looking for. So it is a minimum. So if you go back, well, actually, what I'm going to do is I'm going to plot something here. So if you plot the graph y equals x squared, so just x squared, and actually I've got to do, what I want to do is come up with the equation of the line that goes through these 2 points, through the point 2 comma 1 half and the point 1 comma 1. This is the point that we were trying to find the minimum distance to. This was the point that is the minimum distance. So if we find the slope of this line, so this is x1, y1, this is x2, y2, so you'd have 1 minus a half divided 1 minus a half divided by 1 minus 2, which is a half, divided by negative 1, which is a negative 1/2. So that's the slope of the line between those 2 points. And then you'd have y minus 1 is equal to the slope, negative 1/2 times x minus 1. So you get y minus 1 is equal to negative 1/2 x plus 1/2. And if you add 1 to both sides, you'll get y is equal to negative 1/2 x plus 3/2. So that's the equation for the line between the point out in space and the point on the curve closest to that point on the function y equals x squared. Okay, so I'm going to plot that as well. Negative 1/2 x plus 3/2. Negative 1/2 times x plus 3/2. And I plot that. And there it is. And I'm going to change the dimensions of this thing to try to make the squares as square as possible. So I'm just trying to make this dimension approximately equal to that dimension. So the point 2 comma 1/2 is right there. The point 1 comma 1 is right there. So that's the distance from this point to that curve. That's the minimum distance, and also tells you, well, we didn't calculate the minimum distance. We just figured out what the point was to give you the minimum distance. Now, what do you think is the relationship between the slope of the tangent line for the red curve here and the slope of the blue line? How do you think they're related? Or what would I say about, what would I call the relationship between those 2 lines? They are perpendicular. Yeah, they're perpendicular. And you'll always find that's true. If you have any arbitrary curve that you draw, that the line between a point in space and another curve will always intersect the curve perpendicularly. That's something, if you ever take Calc 3, you'll use quite a bit, because there, I'm going to read in, there's a section here. Let's see if I can find it here. So it's things called like tangent planes and normal lines. And what you do is you try to find the distance from some arbitrary point in 3-dimensional space to some 2-dimensional surface. And I don't know exactly where it is, but anyway, that's something you do in Calc 3 if you ever take Calc 3. Let's actually just see if that works. Let's pick some other arbitrary function. Let's say it's y equals x cubed minus 3x plus 4, and we'll plot that. See what that looks like. And if I picked a point here in space, the point on this curve that's the closest to this point, if I drew a line, let me just put this into Smartboard. Hopefully it'll be the right dimensions or the right aspect ratio. So take that. So if I just pick some arbitrary point in space, like right here, and I take a line, and I draw a line from here, what I would do is all I have to do is look for the case where this line is perpendicular to the red line. Well, it's not perpendicular to there, it's not perpendicular to there, it's going to be perpendicular about right there. And so this distance here would be the minimum distance. When this is a right angle to the curve, you get the minimum distance between the 2 points. If I took another point out here and I drew a line from that point, the point where that line is perpendicular to the red curve gives you the minimum distance between the two things. Okay, so let's look at the next problem on your sheet. It says a rectangle is bounded by the x-axis and the semicircle y equals the square root of 25 minus x squared. What length and width should the rectangle have so that the area is maximum? So we're trying to maximize the area. So we need to figure out, based on the variables x and y, what is the area of that rectangle? Anybody have any ideas? Hannah. Okay, what's the area of a rectangle? Length times width. Okay. So if you take that box and you look at the rectangle that's from the origin to the point x, y, what's the width of that box? Pardon me? It's either x or y. Let me draw the picture. So I'm going to draw a circle. So here's my circle. Here's my, let me move this out of the way. Here's my axis. Here's the x-axis. Here's my y-axis. Oops, I'm going to push this button. So here's my y-axis. And I draw a rectangle within that circle like this. I'm going to take this point and I'm going to do that. And we're only looking at the top portion. So the coordinates here are x comma y. So what I was asking was, what was the area of this rectangle? So the width of this rectangle is what? In terms of the coordinates. Well, don't use just in terms of the coordinates. X, yeah. And the height of the rectangle is y, okay? So if I wanted this, so if the area of this part is equal to x times y, then what's the area of this whole thing? X times y times, these are symmetric, 2, yeah, okay. So the area of that rectangle that we're looking at is 2x times y. Okay, so that's your primary equation. What's our constraint? What's the relationship between x and y that's constraining the whole thing? It's y equals the square root of 25 minus x squared. That's the other equation. That's what's limiting. So you can't use 4 because it's just showing you 4, but that's not the answer. Okay. So it could, x and y could be here. It could be x and y can be anywhere along here. So this is your primary equation. Your secondary equation is going to be y is equal to the square root of 25 minus x squared. So substitute in to make it in terms of x, and then take the derivative of that expression with respect to x. Okay. So at least do the substitutions. And you can see the 2 really doesn't make any difference in the long run, because if you maximize the area of the smaller rectangle, the x times y rectangle, you maximize the area of the entire rectangle. So the 2 will end up, when you take the derivative, will be irrelevant. But go ahead and leave it in there for right now. And then once you make the substitution, then you're going to have to take the derivative. You're probably going to have to use the chain rule to do that, or the product rule, and the chain rule. It's kind of like one of the problems we had on the test. So yeah, I think you're going to have to use the product rule and the chain rule, like we did. There is one way to not have to use the product rule. So let's think about that. See if anybody can figure that one out. So so I've got this. So does anybody know what we can do to, so Evan, what could I do to that expression before I took the derivative to maybe make it a little easier to take the derivative? Yeah. So what you do is you could put x under the radical, so it would become x squared. So instead of having to use the product rule, I just have to use the chain rule. So you end up with a is equal to 2 times the square root of 25x squared minus x to the 4th. And I guess, thinking about it, can we do anything more based on what we just did in the previous problem? Instead of trying to maximize 2 times the square root of 25x squared minus x to the 4th, what can we maximize? How about 25x squared minus x to the 4th? Okay, so we've made the problem a lot easier if we don't have to include the square root. So, you know, if we said a star is just something that I'm trying to maximize, is 25x squared minus x to the 4th. If we maximize that, then we maximize the square root, which means we maximize the area. And that's a lot easier to do. So take the derivative of that with respect to x and find the values of x, which make that go to the derivative go to 0. And remember, x has to be positive. So what do you got? Have you taken the derivative yet? Okay. So now what can we do to factor that? What will be the first thing? Do we have a common factor? X. Yeah. So factor out x. And then so that one solution is x equals 0. That'll give you the minimum, which is 0 area. And then you can solve this one for x just by doing the algebra. Okay, so it's 4 till 5 till 9, so since we have our physics thing coming up, why don't you just hold off on that till tomorrow. Go ahead and put your stuff away. Make sure you spread yourself out so there's space between everybody. You've got plenty of time because Mr. Watkins is going to come, so if you want to take a little break before you start the physics thing, that's fine too, but what I will do is I will put the tests up here, and you can just grab one when you're ready to start, and you're appropriately positioned that you're not sitting next to anybody.